Okay, hello everybody. Let me make this bigger. All right, so we are doing the notes that you guys never had for the assignment that I gave you that you couldn't do. I'm really sorry about that. Okay, so let me get a good little pen. Here we go. So I think this is like the coolest. Hopefully you guys do too. All right, so we're talking about volume of revolution. So basically calculating volume using integrals. And we do this by revolving a curve around an axis or a line. The first thing, most of your marks will come from setting up your integral. Okay, you'll use the correct application or setup okay, sorry, I am just not thinking. So setting up your integral, one of those aspects is using the correct application or setup. And the two ways you can set it up are for area. Y'all, I ordered new whiteout. Amazon just hasn't delivered it yet. Oh my goodness. Area, volume. I'm sorry. Okay, so we can do area problems, we can do volume problems. You just have to make sure you set it up the right way. And the other thing is checking that you have the correct bounds, function, and notation. Okay, so you want to make sure that you have the correct bounds, the upper and lower limits on your integration, your function on the inside of the integrand, and notation. So you need to write all this out correctly. Okay, so setting the integral equal to the correct value. This value will be given in the problem, okay? And it doesn't always have a value. Sometimes it'll ask you to calculate the value. It just depends. And then you may get a few marks for actually integrating and solving correctly. But the bulk of this is from your setup. So make sure that you're setting up well, okay? All right, so we're gonna start off with volumes, then do areas, and we have a bunch of practice on the back. I'm gonna go ahead and do all the practice with you because I want you guys to be able to go ahead and do the around the world. And this is all we're doing today, okay? So we have our first example right here. It says the region R is between the curve y equals the square root of x, so this guy right here, and the x-axis from 1 to a. So I have the picture drawn out for you. On the back, none of the pictures for the examples are drawn out. You need to draw these pictures. These pictures are what is going to help you understand what function you're looking at. Okay, so we already have our picture drawn out. It tells us that the volume of the solid formed is 4 pi. Also, if you're confused and you're like, how does this form a solid? What it's basically doing is it's rotating our function around and it's creating a thing like this where it has, it's like a top almost on its side, okay? So we're making our function spin around this x-axis. Doesn't really matter which way, I just picked that way. And it creates this solid like this. But we're only taking the chunk that's shaded right here, okay? So it would be like, oh man, I messed this up. Oh no, no. Just this guy right here, okay? So like, not that piece or that piece, just that guy. Sorry. Okay, so it says to find the value a. Okay, so imagine taking a slice off of each one of these things. When you take a slice, you get a circle. And the radius of that circle is defined by the value from our x-axis all the way up to our function. Now our function has a y value of f of x, okay? So our function is actually defining like how long our radius is, okay? So if I'm looking for the volume, let's just imagine of a cylinder, I'm basically taking my radius, which happens to be f of x, or I'm sorry, not a cylinder, I'm saying circle. If I want just the area of this particular circle, I'm going to take my radius, which happens to be f of x. I'm going to square it and multiply by pi, right? The area of a circle is pi r squared. And what I'm doing is I'm integrating that to take each of these areas and extend it all the way down from 1 to a. Okay, so my equation for my volume in general is going to be pi times the integral from a to b of our f of x squared dx. Okay, so this is our volume in general. For this specific problem, we have our volume, it's 4 pi, and that's going to be equal to pi times the integral. We're going from 1 to a. Remember, we're squaring our f of x. Our f of x is the square root of x. And then with respect to x. Okay, so again, I'm going to try to explain this one more time. We're calculating our volume by taking individual areas of circles where the radius is defined by f of x. So we're squaring our radius and multiplying by pi. And the integral takes it all the way along and extends it between our boundaries. Okay, so we're adding up all those areas to combine to make a volume. So this should give me that 4 pi is equal to pi times the integral from 1 to a of x dx. When I actually integrate this, I get 4 pi equals pi, and I'm going to have x from 1 to a, 1/2, I'm sorry, x squared from 1 to a. Okay, and so now I need to actually apply that to this piece right here. So I'm going to have 4 pi equals pi, and then I'm going to have a, I'm going to sub in first, so 1/2 a squared minus 1/2 times 1 squared. Okay. Now my whole goal was to solve for a. So notice this pi is multiplied by every term over here, and we have a pi over there. We can just cancel those, get those out of the way. So we get 4 equals 1/2 a squared minus 1/2. Okay, add 1/2 to each side. So I get 4.5 equals 1/2 a squared. Multiply both sides by 2. And I should get 9 equals a squared. Take the square root. A is plus or minus 3. Now, if you look, a was here. I've covered it up with a lot of things. But a was clearly the positive value. So we know that a equals positive 3 is the correct choice. Okay, so there's our first volume of revolution problem. Yay! And now here, in example 2, we're going to do an area problem. So it says the region R is shown below. It's bounded by this curve and the x-axis from x equals 0 to x equals a. Given that the area is 3 natural log of 9 square units, find the value of a. So this one, we're just setting up like a regular old integration, finding the area under a curve problem. So I'm going to have the area 3 natural log 9 is equal to the integral from 0, because we started at 0 this time, to a of 6 over 2x plus 1 dx. Okay, notice we have stuff on the bottom here in the denominator, and it doesn't have parentheses all the way around it, but we could put them, and if we did, it would have a power of 1. Okay, so this means that we're going to integrate and get natural log there, which is nice. And it also means that we could do some u substitution here. So I'm going to make my u 2x plus 1. My du would be 2 dx. And then I want to look, I have 2 dx here, and I want to replace it. I have 6dx here. They don't match. Our goal is to get them to match. In order to turn this 2 into a 6, I would have to multiply it by 3. So I'm going to multiply this whole thing by 3. So 3 du is equal to 6 dx. Now I can replace the 6 dx with the 3 du and also this u right here. So I'm going to rewrite my equation. So I have the integral from 0 to a of 3 over u du. Okay. Now when I integrate, I get 3 natural log 9 equals 3 times the natural log of u from 0 to a. I want to sum my u back in. So 3 natural log of 2x plus 1. Oof. I really need that white out. That's supposed to be a 2x. Okay. And it's from 0 to a. So I have 3 natural log 9, 3 natural log, I guess maybe I should do this, put parentheses, 3 natural log of 2a plus 1 minus the natural log of 0 plus 1. Okay, this thing is going to turn into 0 because it's the natural log of just 1, and the natural log of 1 is 0. And so I'm going to end up with 3 natural log of 9 is equal to 3 natural log of 2a plus 1. Now, there's some convenient things here. Notice I have a 3 on both sides that I can cancel. And also, I could raise both sides with the base e. So e. And I would get that 9 is equal to 2a plus 1. Subtract 1 from both sides. I'm going to come over here. Sorry. 9 minus 1 is 8. 2a, divide by 2, a is 4. Okay, sweet. So we found a. All right, so we've done it with volume, we've done it with area. Hopefully my explanation wasn't too shabby. All right, let's flip it over. Okay, so here's another picture showing us the region bounded by f of x. All right, so f of x is here, and the x-axis from A to B, and then we have a picture of our solid when we rotate around. Hopefully this is a better picture than what I had, okay? So this is really just a picture showing us